Okay guys, this is part 2 of the lesson, so let's get into it quickly. So last time, well actually minutes ago, we just talked about the structural features of a detergent molecule. Bear in mind there are two very important parts. One is hydrophobic hydrocarbon tail, which is non-polar, soluble in oil but not soluble in water. We have a hydrophilic ionic head. So this head can dissolve in water but not dissolve in oil. The ionic head usually is negatively charged, but it can also be positively charged. Okay? And having these two structural features enable it to have wetting properties and emulsifying property, which we are going to talk about it now. So on the right hand side, the wetting property. So what do you mean by wetting property? Does it mean it makes something wet? Now the idea is a little bit different. So you can imagine maybe during, let's say, the dawn, right, early in the morning, the weather is kind of humid, so you may have seen some water droplet form on a leaf, right? And that, so what I'm talking about is having a leaf, okay, like this, and then you will see kind of like a water droplet that forms, okay, that on the surface, okay, you will see some kind of water droplet. And when you see it closer, you notice that actually it looks like a little sphere, looks like a little ball, right? Instead of lying flat, it's kind of formed itself into a sphere. The reason why it forms a little ball, little sphere, is because of something called water tension or surface tension. Okay, surface tension. So for water molecule, it is known to have a very high surface tension. So you can understand surface tension as a tendency to have the molecule join together, not willing to stretch over, not willing to separate. Okay, and water is known to have a very strong surface tension because of its extensive and strong hydrogen bond. So it tends to pull the nearby water molecules together, not willing to spread open. So looking at the water droplet here, so why it forms kind of a spherical structure is because of the tension on the surface kind of pulling the water molecule together, especially towards the center of the droplet. And because of all this force acting towards the center, it results in a spherical shape. Right? Now let's also explain it in form of a diagram. So you notice here, this is what a water droplet, a water bead looks like. So you see all the water molecule on the surface, they have very strong hydrogen bond between each other. So they kind of tighten up the surface, not willing to spread open. Because if you think about it, if it's going to spread open, it's going to break some of this hydrogen bond. So it's going to be needing more forces, more energy to break them. Okay, so we say that the strong hydrogen bond tightens up the water bodies, preventing it from spreading over. Now, since it does not spread, so that means it doesn't wet the surface, right? Because you think about it, if this water droplet is able to spread over the surface, then the surface will be wet. So this one, because it tightens up itself into a sphere, it does not wet the surface. Therefore, we say that with a high surface tension, it doesn't wet the surface. Okay? But if you go back to the subtitle here, wetting property. So basically, the detergent has a property to make something wet. That means to prevent water from tightening it up, basically the detergent will make things wet. By making things wet, that means it will reduce the surface tension and resulting in the water droplet being able to spread over the surface. So this is why it is called wetting property. Okay, now look at the next diagram. Now if you introduce some detergent molecule, so the detergent molecule kind of dissolve into the water droplet only at the head, because the head is water soluble, the tail does not. So once you add inside, so you look at the thickness of those arrows. So originally they have a very thick double-headed arrow, meaning strong hydrogen bond between water molecules. But now with the introduction of detergent molecules, it kind of weaken the force holding the surface molecule together, right? So we say the solvation. Solvation means with the detergent molecule being surrounded by water molecule, it weakens the overall strength of hydrogen bond. Okay? So basically, water cannot form hydrogen bond with the salt, with the detergent molecule. Okay? So that's why the overall strength is weakened. And because of the weakening of the surface tension, so the molecules, the water droplet can no longer maintain its rounded shape. So it kind of collapses due to its own weight, and therefore spread over and wet the surface. Okay? So the water body collapses and spread over due to its weight. So this is what the wetting property is talking about. Okay? To be honest, this is a reference part, so you don't really have to learn too much about it. All you have to know is detergent reduce the surface tension of water, allowing to spread and wet others. That's why it's called wetting property. And right now I have a little demonstration, which is a very classic experiment. Hold on a second. Okay. Right. Well, so basically, what we have is this is a detergent. You can see a detergent here, and then I have a large beaker of water. We have a smaller beaker and a glass rod. So first of all, I'm going to add a pump of this, okay, into the smaller beaker. And then I want to add some water. And then basically I stir it to form a detergent solution, which I will use it later. Okay, so this is a detergent solution. And then here I have an evaporating dish. So to that I will add some water. Okay. And then I will find myself a little chalk, a red chalk. So chalk is made by calcium carbonate, it's insoluble in water. So what I'm going to do is I find myself a little scissor, and I'm going to kind of peel and scratch some of this chalk powder in it. So as you can see, the surface turns a little red. I can add a little bit more so that you see more clearly from the visualizer. Okay, can you see the red color, okay, which is evenly distributed on the water surface. Now, you notice water has a very high surface tension, so it's kind of maintain its surface tension, just like a layer. You can imagine like a tightened layer on the surface that doesn't break at all. So, and right now, the chalk powder kind of sitting on top of this layer. So this is what we expected to see. Now what we are trying to do is, with a detergent solution, right now, I'm going to dip the glass rod onto the surface and see what happens. Now I can do this with maybe a ball pen first. Maybe a ball pen, okay. I can dip it into water and then dip it on the surface. So you see, there are no observable change because the water does not affect the water tension of the water. They are the same, right? So there are nothing happening, okay? Nothing happening, right? But with the detergent molecule, with the detergent solution, where I have some detergent at the tip, look what happened when I dip it down. Can you notice what happened? Can you notice what happened? So, as you can see, the chalk powder kind of move outwards away from the center. So it kind of like breaks apart. So what it does is the detergent that I just dipped kind of weaken the surface tension of the water. So that layer of water on the surface kind of break down, kind of no longer hold its strength. So when the layer kind of break down, it spread over the place, and as it spread over the place, it also carry the chalk powder to the side. And that's why you see the chalk powder kind of spread to the side, showing how the water molecules move. Okay, so this is a very classic experiment showing how detergent can reduce the water tension. Okay, so here's a very simple demonstration. I'm going to move this away. Okay, coming back to here. So that's the idea. Now down here is more important. It's about the emulsifying property. If you study biology, you should have already learned. Emulsifying is a process to make some oil into oil droplet, which are more soluble in water. Okay, if you learn about it in biology, you know the biosalt. Biosalt is able to emulsify fat into oil droplet, which can speed up, increase the surface area for the enzyme lipase to act on the lipid, and therefore speed up the rate of digestion of lipid. Okay. If you look at this diagram, as you can see, water and oil does not mix. So in order to make it mix, we can add some detergent molecule. Now when you add the detergent molecule, you will notice that the detergent molecule will arrange themselves in this way, such that the hydrophilic ionic head facing down to the water layer, and the hydrophobic hydrocarbon tail kind of insert itself into the oil layer. So basically, like dissolved light, they dissolve to the solvent that they like to dissolve. Very simple. Now, once you add the detergent molecule, what we do is to shake it, or you stir it with a stir rod. And once you stir it, the oil will be broken down into oil droplet. And the oil droplet will maintain as a little spherical shape, because as it forms a droplet, this is how the detergent molecule will arrange on the water droplet surface. And as they form into this shape, you notice that this is the most stable form of how the oil can arrange. Because the key is, you notice here, the ionic head is negatively charged. So obviously negative and negative will repel each other. So if the hydrophobic part is inserted into the oil, and basically it will bring the negative charge in close distance. So think about in what shape an oil can adopt in order to separate this negative charge as far as possible. Would that be a rectangle? Would that be a triangle? Or would that be a sphere? So mathematically, it tells us that forming a sphere is the best way to separate the charges, the adjacent charges, away from each other. So that's why the oil will adopt a spherical shape upon shaking, in a way to separate the charges as far as possible. Okay? So that's why when we shake it, it will form this kind of oil droplet with a negative charge spread over on the surface of the sphere. Okay? Now, you also notice that this oil droplet now, they're bearing a negative charge. So it is soluble in water. It is soluble in water because it has a negative charge. Now, you may also ask, will this small oil droplet join together, combine together to form the thick layer of oil again? Well, the answer is obviously not. simply because now they all have the negative charge, they kind of repel each other. So the oil droplet can no longer rejoin to form the thick oil layer. So that's why the oil droplet maintain as a droplet form. Now, if you do not add the detergent upon shaking, very quickly the oil droplet will join with each other and then go back to its original thick layer of oil, because that would be the most stable configuration. You can think about it this way. So, but adding detergent allows the formation of stable oil droplet that does not join together at all. Okay, and the advantages of this is now you have so many tiny droplets soluble in water, so it will be easily washed away by water, and that's why detergent can fulfill its purpose of aiding in cleaning or washing dishes. They just convert any oil stain into oil droplet soluble in water, and therefore can be washed away by tap water easily. Okay, so that's the idea. Now let's go through the test quickly. Now the water and oil do not mix, however adding detergent allow the water and oil to mix, okay, to form a stable emulsion. Okay, an emulsion is a very stable mixture of oil and water. You can think about it this way. Okay? It's a mixture of two or more liquid, which at least one liquid exists in a tiny droplet. And in this case, the tiny droplet is talking about the oil droplet, of course. Okay, and dispersing throughout the rest of liquid. Okay, so that's the idea. Okay, so like I said, the negative charge on the surface allows oil to dissolve in water, easily washed away by water. Okay. Also, the repulsion of the negative charge prevents the droplet from joining with each other, and therefore a stable emulsion is allowed to exist. Okay, so this is the idea. Now you need to know how to draw this one. Okay, you need to know how to draw this one. So probably the test or exam may ask you to illustrate the oil droplet and how the detergent arrange itself. So make sure you know the hydrophilic head, ionic head must be on the outside, and the hydrophobic tail must be inside the oil droplet. Okay, and you must also label the parts. And what else do you have to know? Okay, nothing at all. Okay, down here, two little remarks. You have learned it in Form 1 actually. Now the detergent will cause water pollution if you discharge too much. The reason is because the detergent, especially the soap one, actually they are food source for bacteria. So if you discard many of this detergent, then the bacteria can use up those detergent as nutrients. They will have a fast growing, huge population, and they may use up the oxygen and endangering the organism living in the water. Also, we will add phosphate into the detergent as a kind of like I think it is used to adjust the pH as a buffer, maintain a very constant pH, I guess. So the pH, the phosphate, actually are nutrients to algae. You should have learned it, and therefore encouraging an algal bloom. So these are some of the pollution caused by discharge of detergent, also the soap. Okay. So go to the next page. Again, we have some practice question for you guys to go through. Quite a lot of the questions. So I guess you need around 10 minutes to finish it off. So similar to the previous video, I would like the subject representative help me to pause the video for a while, for around 10 minutes. I guess I'll give you 10 minutes to work on this, and then I will discuss the answer with you guys. Okay, so 10 minutes, please pause the video. Okay, coming back. So after 10 minutes, I hope you guys have attempted some of the questions. So let's look at this question. Now this is This is a question about castor oil. The structure is given like here. It is a triglyceride or triester with a fatty acid, and the fatty acid itself has a hydroxyl group and also a CC double bond as well. Identify all the functional group present in compound X. So first of all, I see ester, must be ester, and then I also see the CC double bond, okay, and then I also see hydroxyl group here. Okay, so these are all the functional group I can see from compound X. Okay, so for part B, it says how many cis-trans isomers do compound X has. Actually, this is quite a challenging question because there are 3 double bonds. So with 3 double bonds, each of them can have its own cis or trans configuration. So how many cis-trans isomer can it form? Now, it's like a mathematical question plus some chemistry. So I tried to work this out quickly using a tree diagram. So you can think about it as having 3 cis-trans isomer, and we look at how many combinations are there. For example, a cis-cis-cis, or cis-cis-trans, or trans-trans-trans, okay? So, for example, for a compound X, so first of all, we focus on the first double bond here. So the first one can be cis or trans. Do you agree? And we look at the middle one, this double bond. So if the first one is cis, then we can have cis-cis, and we can also have cis-trans. Do you get it? So this one is talking about this one, the middle one. Now, for the first one being trans, the second one can be cis. The third one can also be, the second one can also be trans. So we have 4 combinations. Now, for the last one, again, it could be cis or trans. So we do the same thing. So we can have cis, 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 trans. And then here, we can have cis, trans, cis, and cis, trans, trans. Same idea, we can have trans, cis, cis, and trans, cis, trans. And lastly, we can have trans, trans, cis, and trans, trans, trans. Okay? So altogether, we have 1, 2, 3, 4, 5, 6, 7, 8. 8 combinations. So does it mean that 8 isomers? Well, not really, because if you notice, this one and this one are the same. They are the same. And they are connected at the terminal of the glycerol. If you can look at the glycerol as the backbone. So that means if you look at some of the combination, for example, if you look at these 2, cis, cis, trans, and trans, cis, cis, they are actually the same. They are actually the same. If this one you flip over, it's going to be this one. So these 2 are the same. So you can delete one of them. Delete one of them. Okay? Similar idea goes for these 2. So cis, trans, trans, and trans, trans, cis. Again, the part that is cis, one is the first fatty acid, another one is the third one. They're the same. If you flip this, then it will form this one. So these 2, again, are the same. So this one, same, same. So you can delete one of them. And the others will be different from one another. So altogether, there should be 6 isomers. So this one, the answer is 6. Yeah, this one is quite challenging. I didn't think about how it is actually quite complicated. Okay. So, outline a synthetic route, no more than 3 steps to convert X into compound Y. So this is Y, okay? You should include all the reagent condition, blah, blah, blah. no more than 3 steps. So this is actually a soap molecule coming from this one. So first of all, I will start from a compound X, to simply put, compound X. So I will first do alkaline hydrolysis. So alkaline hydrolysis, I will use NaOH and I will heat it, and basically I will have so this one will be cut, and I will have this part remain. So I'm going to copy this part, the whole thing down in the form of a carboxylic ion. So it's going to be okay. So just direct copy. Now you notice that this one, when compared to this one, if you want to count the number of carbon, they should have the same number of carbon. So what we have to do is to get rid of the double bond and the hydroxyl group. So first of all, we can get rid of the hydroxyl group by undergoing a dehydration reaction. So we can do Al2O3 heat, which is to dehydrate this one into an alkene. So you can have, and then the whole thing copied again, and then we have a CH, and then, well, I do not have enough space, H2, 5, CH3. You need to make better use of the area. So basically, we are dehydrating this one, the hydroxyl group here, into a double bond, and then lastly we will form our product, which I can directly copy from the top. I will do a hydrogenation with PET. Okay, I will do a hydrogenation. So this is how it works. Okay, compound Y aid cleaning, aids cleaning, explaining whether it's a soap or soapless detergent. So, of course, this is a soap. But how do you explain? Well, because it has a carboxylate group. Carboxylate group. Now, I was expecting carboxylate or ion of carboxylic acid, but I will not accept carboxyl group because it is not a carboxyl group. It is a carboxylate ion. Okay, so carboxylate group. Okay, so here, when compound Y is shaken with a mixture of oil and water, a stable emulsion is formed. Explain how compound Y can form a stable emulsion. A suitably drawn diagram is also acceptable. So I will go for the diagram. I'll draw it again. So with the anion head on the surface, using a sphere to represent, and then the tail, like this. Okay, and you have to label it, of course. This one is the hydrophobic hydrocarbon tail. This one is the hydrophilic ionic head, and you will label this one as the oil droplet. The outside should be water. Okay, so this is how it works. If you are trying to use words to explain, so you need to tell me about, first of all, the structural features of compound Y. Okay, with the hydrophilic head and hydrocarbon tail, this is 1 mark. And then you tell me the arrangement of the compound Y in an oil droplet. Okay, so which one dissolves in which one. And thirdly is you tell me that it forms an oil droplet that is soluble in water. Okay, so this is what you're going to do. Now 4, explain why compound Y loses its cleaning ability when it is used together with the following solution. So if it is used with calcium chloride, so the key is it has a calcium ion here. So the calcium ion, okay, we would say compound Y, okay, reacts with calcium 2 plus ion, okay, to form insoluble precipitate. Okay. So once it is formed precipitate, it is no longer soluble in water, so it cannot exert its function. Okay. So it reacts, I think it is 1 mark, and insoluble precipitate, another 1 mark. Now the next part is what about dilute hydrochloric acid? Now in a very acidic medium, so the compound Y here, can it still maintain its ionic form? No. Basically, this one will be converted back to the sulfuric acid. Sorry, convert back to carboxylic acid. Okay. So once it's formed back to carboxylic acid, then does it still have the hydrophilic ionic head? No. So that's why it cannot exert its function as a detergent or soap. Okay, so that's why you would say compound Y will be converted to carboxylic acid, which loses its hydrophilic ionic head. Okay, or you can say which is only slightly soluble in water. Okay? So the key is it will convert back to carboxylic acid, so loses the hydrophilic ionic head, or it is only slightly soluble in water. Okay? So that's why it can no longer exert its cleaning ability. Okay? All right. Now for the last question, which of the following compound cannot work as a detergent? So detergent you need to know is it should have a sulfate anion head. So this one and this one should do the job. And for this one, it is not a sulfate. It is a kind of like an ammonium, a tertiary ammonium ion. But it is still work because you remember for detergent, this one could be negative, could be positive. Now for this one, this is a carboxylate ion. Carboxylate ion. And this is actually a soap. Okay, this is a soap. If you have hard water, it will form scum. So that's why it doesn't work as a detergent. So the answer is A. Okay? So that's it for the lesson. So yeah, I hope you have learned something. And if you have any problems, if I didn't explain properly, you can ask me later. And the next lesson, we will be focusing on the last part, which is condensation polymerization, and then we will enter energetics. So that's it for today. Bye-bye.